Hi everyone. Please write yes if you can hear me and you're seeing my screen. Great, perfect. So we have 54 people today, which is great. And let's start. So the learning goals for today are the following. We will cover what are coordinate systems, how can we convert between coordinate systems. We also see how can we use coordinate frames or coordinate systems as transformation using transformation matrices, and we will also cover the several linear transformations by rotation, scale, and reflection. Okay, that is basically what we need to cover today. And the PDF is already on the webpage as always. However, I will ask you a couple of questions on the lecture. So the answer for those questions are not in that PDF. So yeah, I will obviously upload the final version later. And then we will have also like two pauses as always, right? Two pauses for questions. Okay, so let's start. So coordinate systems. So having a point P like this, right? And imagine that we have a grid in which we have different coordinate systems. So the coordinates of a point, like in this case the point P, with respect to any coordinate frame are basically scalars from the basis vectors from that coordinate frame. So basically a coordinate frame, let's imagine this world that is in 2 dimensions. So the coordinate frame F1 has two basis vectors, I and j, right? And the point P is just, or the components of the coordinates of the point P are scalars from those basis vectors, right? So in the end, the position is then the sum of those scale basis vectors, the scale version of those basis vectors, plus the coordinate frame's origin. So let's see this, for example. What are the coordinates of the point P with respect to F1? And here we are going to use the chat. So try to write your answer in the chat. What do you think? What are the coordinates of those? Yes. 4 times A and 1 times J, of course. And so it's basically 4, 1. Yeah. Basically what we are doing here is we're scaling or multiplying 4 times this basis vector I, right? And we only need 1 times this vector J, and we are basically making a sum, right? We are adding these vectors. Okay, good. In this case, because this coordinate frame in the end has its origin, and its origin is basically 0, 0, 0, we don't need to add anything else. Okay, so in this case, we don't need to add anything, because if we add the origin and the origin is 0, 0, at the end the coordinates is basically the same. Now let's see what happens with this coordinate system. Now the basis vectors are different, right? So the I coordinate, basis vector, sorry, is this one, the red one, and the j is this one, and they are rotated and also scale. So what do you think are the coordinate system, sorry, the coordinates for the point P with respect to the frame 2? 1/2 and 5. Okay. Yes. Why would you use non-orthogonal basis vectors? Yeah, very good question. That's the thing. You will see why it's important. The thing is, the basis vectors of a coordinate system, they don't need to be orthogonal, okay? And they don't need to be unitary. For some transformations, that we will see that later, but for a certain type of transformations, they need to be orthogonal and they need to be unitary. But in general, a coordinate system can have any possible shape. Okay, so I think most people is getting the right answer, right? So we need to get half of the I vector, right? And 5 times the J vector, okay? And this can be confusing sometimes, that like, okay, why is 1/2, right? In the end, it seems that in this case, that the I vector has 2 units length, right? for some people, right? Because in the end we have this grid and it seems that it has 2 units, right? So why isn't this like 1 unit, right? So the thing is that the basis vectors of a coordinate frame are always unitary in their world, right? So their world is basically like the grid, right? So in this case, this grid is not exactly the grid from this coordinate frame, because in reality, a coordinate frame distorts its own world, right? Distorts its grid. So this would be the actual grid from this coordinate frame, right? So we can see again, right? We need to multiply the j time 5 times, right? And this is half of the entire length of the I vector, right? The thing is, this visualization could be very confusing, right? So when we are working with coordinate frames, we usually use a grid, right? That is basically a fixed grid, and it will be incredibly confusing to use like all the distorted version for every coordinate frame. But yeah, but keep in mind that the basis vectors of a coordinate frame, they're always unitary in their own world, and basically the world is distorted, right? So what about this one? What are the coordinates of this one? 1, 3. Yeah. Exactly. Yeah. So it is easy, right? It is, frankly, yeah, it's very easy. Okay. So now let's see another example. What happens here? What do you think? What are the coordinates for this coordinate system? Does not compute, does not exist. Yeah. Why? Do you know why? It's not independent. Yes, exactly. We have these beautiful mathematical answers, right? Yes. So what happens here is that these the two basis vectors are a scale version of each other, or we can also say that those basis vectors are linearly dependent, right? So they're not independent, as William is actually saying. Yes. So in this case, the world of this coordinate frame, right? The distorted world of this coordinate frame is basically collapsed in a single line. Again, we are not seeing that because I am using the same grid for everything, but imagine that it's like having the entire grid and it's basically collapsed in a single line, right? So P is actually outside of that space. So it's not possible to define a set of coordinates to achieve point P from the space that is here, right? Because everything is collapsed. So if, for example, we create a matrix with these basis vectors, right? What would be the determinant of that matrix? Who can answer that? 0, exactly, because everything is collapsed, right? So the determinant is basically the area that is spanning by the vectors of a specific, I mean the column vectors of a matrix, right? So yeah, exactly. This will be basically 0 for a determinant. So yes, so they're undefined because the vectors are linearly dependent. So the frame space is collapsed and P is outside. Okay, another question for you. If the coordinates of a point can be defined in a coordinate frame, are these coordinates unique? What do you think? Think about it. If P is on the space, right? The space is not collapsed and P is inside the space. Are the coordinates always unique? Someone is saying that maybe it depends if it's orthogonal or not. Someone is saying, I think yes, yeah. Okay, anyone else? Okay, someone is talking about polar coordinates. Okay, let's not talk about polar coordinates right now, where we are in Euclidean coordinates. But yeah, exactly. So yes, if the coordinates are defined, right? If the point P or the vector, right? The vector for the position P is inside that space, the coordinates are always unique, right? If they were not unique, we would have a lot of problems in computer graphics, a lot of problems, and the world would be very weird if they were not unique, right? However, you will see that there's one specific type of coordinates called homogeneous coordinates. They will see that eventually that it's kind of, it has kind of this idea that is a point in a certain space can have different coordinates, so they're not exactly unique. But those are homogeneous coordinates, and that is basically, I think that is our next lecture. Okay. Okay, someone is asking, does unique mean a set of coordinates cannot refer to multiple points? Yes, this exactly. The set of coordinates, they cannot define multiple points. They are only defining a single point. A point cannot have multiple. Yeah, basically it's the same. Also, it also means that a single point cannot have multiple coordinates, right? Yeah. Okay. So now let's see how can we basically make a conversion between coordinate frames, right? So because in the end, a coordinate frame is like a world, right? And we can have a position with respect to that coordinate frame. But sometimes we need to convert from one coordinate to one frame to another, okay? So we have two coordinate frames. We have A, that is basically similar to what we usually understand, like the X and Y, or in this case, I and J, right? And they are both unitary vectors, and they are orthogonal, and they are, yeah, basically similar to what we usually expect. And we have this other coordinate frame, and the basis vectors are basically rotated and also scaled, right? So let's imagine that we have a point P with coordinates with respect to B that are 1, -2. Okay, we can see the coordinates here. So in this case, we need to go back on J, right, 2 times. So that is why it's -2, and we only need to go further in I direction only 1 time, right? So this is the coordinate 1, -2. And again, if we had the actual distorted grid for this coordinate frame, maybe it could be easier, but for now let's just keep this grid, right? And we can also see that, of course, the actual coordinate from the basis vectors with respect to B on their own distorted world are 1, 0 for I and 0, 1 for J, right? Because they're always unitary, okay? So now let's see how can we make a conversion between coordinate frames. In this case, having a coordinate frame that is based on one frame that is B, and how can we convert that one into the coordinate frame A? Okay. So what we do, what we do is this. We need to first get the coordinate frames, the coordinates from the basis vectors of B, but with respect to the coordinate A. Okay, so in order to make the translation, we need to get the original grid, the original coordinate frame A, right? Remember, A was like, this was I and this was J, right? So the coordinates with respect to A from the basis vector I are 1, 1. The coordinates of the vector J with respect to the coordinate frame A are -1, 2. Okay, so we create a matrix in which, the column vectors, the columns of that matrix are basically the vectors I and J with respect to the coordinate frame A. Okay, and then we multiply that matrix times the position with the coordinates with respect to B, right? So these are the coordinates that we have right now with respect to B, and these are the coordinates, right, of I and J column vectors, in this case with respect to A. So the result will be 3 - 3, which is the position of this point. It's exactly the same position, but now in the coordinates of A. Okay, do you have a question about this? Is this clear? And again, remember, you can write under chat, or also you can raise your hand. Yes, this is assuming that they both have the same origin, of course. In this case, they both have the same origin. Good observation, Luis. Thanks. Okay, where did 1 minus 2 come from again? Great question. So again, let me go back. 1 minus 2 is the position of this point, are the coordinates of this point, but with respect to this coordinate frame B, right? So this is probably clear, right? You need to go back on this direction. You need to go back. You need to go to negative sign 2 times, right? And you need to go back. You need to go further in this direction only 1 time. So basically, 1 minus 2 are the coordinates of P with respect to the coordinate frame B, right? So the translation is making a matrix whose columns are vector I and vector J, but in coordinates of A, right? And multiply by the original coordinates of P that were on the coordinate frame B, right? So you do that multiplication, and what you get is basically the new coordinate frame, the new coordinates, sorry, from the point P, but now with respect to A, okay? Very good question. Why do we need to convert between coordinate frames? Beautiful question, Timothy. This is what this is super important, because converting between coordinate frames is basically what the vertex shader does, for example, to take the original coordinates from your model and then convert them into the world coordinates, and then to convert them again into the camera coordinates. So remember, I mean, I'm still not explaining that, okay? But remember that the main goal of the vertex shader is basically taking the original coordinates from your frame, from your vertex, and basically convert them into screen space. That is basically just converting those coordinates between different coordinate frames. So that is why we need them. Yeah. Okay, so Kai is asking, so multiple points cannot be defined on the same coordinate, correct? What? Sorry, I don't understand. Multiple points cannot be defined on the same coordinate, correct? Well, I mean, for the same coordinate frame, you can have multiple points defined on the same coordinate frame, of course. I don't understand the question. What we said is that on a single coordinate frame, a single point will have a unique set of coordinates, right? Okay, can I continue? So this conversion from B to A is clear? Is this clear? Say yes if you think it's clear, please. Okay. Okay, perfect. Yeah, many people is saying yes. Great. Okay, so now let's see what we do in the case of doing exactly the opposite, right? So now having the coordinate A, or with respect to A, and then translate it to B. So basically having the 3 minus 3 and convert it to the 1 minus 2. So we take the same matrix, and basically we take the inverse of the matrix, right? And here we need to understand something. A transformation matrix, right, is basically like taking the space and distort that space, right? It's literally applying a transformation. So the inverse of a matrix is basically like playing back the same transformation, right? So if, for example, we take a rotation matrix that basically rotates the entire world by 45 degrees contraclockwise, right? The inverse of this, exactly that same matrix, right? But the inverse of that matrix will basically get everything back 45 degrees, right? So the inverse of the matrix, in case of transformation matrices, it's just playing back the transformation. So in this case, if you take the inverse of this matrix, and you can do these computations at home, if you take the inverse of this and you multiply by this vector, which is the coordinates of P with respect to A, right? Then you get the coordinates of P now with respect to B, okay? So now, that is how we can basically go back and forth between different coordinate frames. A non-invertible transformation matrix use? No, we never use non-invertible transformations. Yes, that is a very good question. Of course, that will be a problem, right? Having a matrix that is, it can be invertible. That is for sure a problem in terms of transformations. Yes, yeah, Ivo is already answering. Yes, exactly. And someone is saying no because the determinant is 0 and hence the world is collapsed. Exactly. Thanks. Very good questions, very relevant questions, and very good answers. Great. Okay, so I mean, we're kind of already doing this, like taking a break and questions. So someone is, does someone wants to raise their hand and use audio, or can we continue? Oh, sorry. So Pavel is asking, how do we know what the matrix values are in this case? So Pavel, are you referring to this matrix, these values, 1, 1, and minus 1, 2? Okay, these are exactly the same. This is exactly the same as before. So remember, the columns of this matrix are basically column vectors from I and J with their coordinates with respect to A. So as you can see, when I am converting from B to A, I have this matrix, and the matrix is not changing. It's exactly the same. The same column vectors are in the matrix. The only difference is that in this case, you apply the inverse of this matrix, right? Yeah. Someone is asking about the camera matrix. Let's not dive into the camera matrix right now because camera matrix is very complicated. So we will talk about that later. Yeah. Okay, good. So let's continue. So now let's see how we can use transformation matrices and use them, or use a coordinate frame as a transformation matrix, right? Use a coordinate frame as a transformation matrix. So let's imagine that we have this coordinate frame A, right? And we have I and J. They are both unitary vectors, of course, because they are in their world. They are also obviously unitary. And they are orthogonal between them, okay? And we have point B. So let's imagine that we have another coordinate frame. And for now, again, these coordinate frames are exactly in the same origin. This is very important. And this coordinate frame is basically just a rotated version of the same basis vectors, right? So the length of this vector I, the one from the coordinate frame B, has exactly the same length as this one, so both are unitary. And these two are also orthogonal, okay? Good, great. So now let's imagine that if we create a matrix with the column vectors I and J from the coordinate frame B, right? But with their coordinates with respect to A, this is exactly the same as we did before, right? If we create that matrix and multiply that matrix times the point P, what we obtain is basically this point here, right? It makes sense. The coordinates, the original coordinates from point P with respect to A were 2, because you need to go 1 and 2 times the I coordinate, right? So there were 2, 0, right? Everybody agrees, right? So basically what you're saying here is, okay, I want to have the same coordinates 2, 0, but now with this different coordinate frame, or these different basis vectors. So now you are doing exactly the same. You're walking 2 times this basis vector, right? So 1 and 2, and 0 times this J basis vector, and you end up here, right? Good. So imagine that because this point here, imagine that we are seeing the tip of this vector here, right? The tip of the vector I, and imagine this like a position in space, and when you are turning this, right, like rotating this coordinate frame, this will be like a point that is moving at a constant speed in a unitary circle, right? So imagine a unitary circle, and imagine that this guy is basically moving in that circle. That means that the x component of this, of the tip of this vector here, right? The x component will be cosine theta. Theta will be this angle here. And the y component of this guy, right? This position here will be sine of theta. Does everyone agrees with this? Everyone agrees with these coordinates? Say yes if you agree. So many people say, oh no, trigo. Agreeable. Yes. The thing is, that is exactly what sine or cosine are. That is exactly what cosine is, right? So if you imagine a point in space that is basically moving along a unitary circle, right? Its x and y positions are exactly cosine and sine. The cosine of the angle theta and the sine of the angle theta are basically the x and y of a point that is an imaginary point that is basically moving at a constant speed in a unitary circle. Okay? And yes, it's counterclockwise, of course. This is rotation that is counterclockwise. I will talk about that later. Yeah. Okay. So if you can imagine that, you can imagine exactly the same for this guy, for the tip of this vector here, right? This vector is basically at 90 degrees from the other one. So imagine that is the same. He started here where, can you see my mouse, by the way? Yes, perfect. So this guy started here, and again, it's a point that is basically, it will begin to move in a circle at constant speed, in a unitary circle, right? So it means that its x and y coordinates will be minus sine theta for the x coordinate and cosine theta for the y coordinate. Everybody agrees? Yes, right? Because at the end, again, that is what sine and cosine mean. Sine and cosine are the x and y components of something that is moving at constant speed in a unitary circle. Okay. So if we take that matrix and we express it as exactly these coordinates, we get this, right? And basically what we are doing here is we are making a conversion between coordinate systems, right? Because that is exactly what we are doing, right? We are creating this matrix using column vectors, multiplying by some coordinate, right? And basically what we are doing is a conversion between coordinate systems. But the result of that conversion is basically a transformation. In this case, it's a rotation, right? This is exactly equivalent to taking point P and basically rotate by theta degrees, right? Do you agree on this? Can you see that is basically the same? Say yes if you agree. Great. Okay, what is an example scenario where matrix application comes into play in CG? Well, a lot of things in computer graphics are basically, well, most of the entire animation world in computer graphics is based on matrix multiplication. Yes, and most of the also the computer graphics things that we need to do in terms of getting vertices and then apply everything in and transform every position of your 3D models and your lights and your cameras and everything, and basically transform everything into a 2D image that can show, for example, perspective. Everything is done with matrix multiplication. So yeah, matrix multiplications and matrix vectors multiplications are basically the foundation of computer graphics. Okay, so everyone agrees with this, right? So if you take, again, this matrix whose column vectors are basically the basis vectors of this coordinate frame that is just turning, right? And you multiply by the original coordinates, what you obtain is this point, is the point P prime, that is basically a rotation by theta degree. Okay, so we can extend this easily into 3D space. This is 2D, but it's very easy to express this in 3D. So imagine, right now it's 2D, right? So 2D, sorry, is basically we have like X and Y. right? In this case, we had I and j. So imagine that now it's 3D, and imagine that now there is a vector that is exactly on the same position of the origin, but it's basically coming toward us, right? It's like coming out from the monitor, right? And we can call that guy Z, right? Because in the end, this is similar to have X, Y, Z, okay? So extending this to 3D world will look something like this. For this column vector here, I mean, for the position of the tip of this basis vector, we not only have an X and Y coordinate, but also a Z coordinate, right? So this guy is on the floor, so its Z coordinate will be 0, right? For this column vector here, which is the tip of this vector, right? We now need a coordinate on Z, and because it's basically flat and it's on the floor, its coordinates on Z will be 0, right? And now we have another column that is basically another column vector, which is this guy here that we are not seeing because we are still seeing a 2D image, but we can imagine that there is a vector here that is pointing toward us, right? It's coming outside to the monitor, from the monitor. And those coordinates will be, of course, 0, 0 in X and Y and 1 in Z, right? Because these are coordinate frames that are orthogonal and also unitary, right? Do you agree that this is an easy extension from what we had? Someone is asking why not pointing inside. Very good question. Again, that is very relevant. This is just a convention in computer graphics, and actually in some books you can see that all their computation and their math is based on defining the Z value as positive going inside the monitor, and in some other books they're defined the positive value of Z as going outside the monitor. Yeah, so there's no right or wrong answer. Different, yeah, some people use the positive inside the monitor, some other people use the negative inside the monitor. Yeah. Okay, any other questions? Okay, where is the 001 comes from? Is it Z-axis? Yes. So this guy is basically, this column vector is this imaginary vector that we are not seeing right now, that is basically coming out from the monitor, right? And it should have 001 as its X, Y, and Z components, okay? So I am asking you to imagine things, but let me show you the actual image. So this is what we have right now, right? So we have a red vector, basis vector, which is the I vector. By the way, can you see the 3 to the max? Yes? Okay, great. So we have the red one, the green one, and basically we have a new one, which is the Z axis, right? So if we have something that is, if we have something like this that is rotating counterclockwise, right? These two basis vectors are basically, they keep their position on the plane, right? And the third axis, that is the one that is giving this three-dimensional extension, is basically just staying there, right? And its coordinates are, of course, so the coordinates of this point, the tip of the vector, are 0, 0, 1, right? Because these are unitary vectors, right? Okay. And again, if I animate this thing, and again, you can imagine that this let me just give me a second. I can, for example, take this point here, which is basically the tip of the vector, and I can ask this software to show the motion path. And as we said, is basically a unitary circle, right? The meaning, as we said, the meaning of sine and cosine functions is just the components or the position on X and Y of an imaginary point that is basically traveling at constant speed in a unitary circle. Okay, good. So let's go back to the presentation, And as we said, this is an extension, basically having this rotation matrix that it was originally, it was not a rotation matrix, right? Originally, it was just, we were just converting from one coordinate frame to another. But because that other coordinate frame, it turns out that the basis vectors are always orthogonal. Those basis vectors are always unitary, are basically the same from, they have the same length from one coordinate frame to the other one. And what we end up having is a rotation, right? So this is called a rotation matrix, and that's why I changed this. Now it says that it's rotation matrix along the z-axis with respect to the angle theta, okay? So the rotation axis is basically the one that it doesn't move or it doesn't change, okay? So in this case, the one that is not changing is the z-axis, right? So exactly with the same concept, we can create, or we can construct the entire set of rotation matrices in 3D, right? So this is the one where we're checking the z-axis, in which we have 3 column vectors, right? They represent the 3 basis vectors of this coordinate frame that is turning. And if it's on z, the one that is representing z is obviously turned off, right? So this one is basically not doing anything, right? For the case of the rotation in x, now the one that is not doing anything is this one, right? Now x is not doing anything, and now the ones that are operating are y and z, right? So this is basically equivalent. Give me a second. Where's my other software? Here. Okay, so this is basically equivalent. I will change the animation. Right, so now this is what you have when you're rotating along the x-axis, right? Now the 2 basis vectors that are moving or rotating, right, are the green and the blue, right? And the x-axis is basically not changing, and it's always counterclockwise. And here we can mention something important. Rotations in computer graphics, they follow a rule called the right hand rule. So imagine that you have your hand basically laid down, your right hand basically laying down on the floor, and basically your thumb is on this direction, and the rest of your fingers are on the direction of the axis, of the green axis, okay? So imagine a hand that is basically in that position. So always the rotation will be in the direction of your hand closing, right? If you start to close your hands, your fingers will like roll in this direction, which is basically counterclockwise, right? So whenever you want to understand, okay, I have a rotation axis, and I don't remember like in which direction this matrix, in which direction will rotate everything, you just need to take your right hand and kind of like align your thumb with that rotation axis that you're using, and that will tell you in which direction you're rotating. Sorry. Okay, and same happens with this rotation matrix, right? The rotation matrix in the axis y, right? So in this case, y is the one that is not changing, and these are the coordinates for the basis vectors that are changing. Okay, so these are the rotation matrices in 3D, and now you know where they come from, right? Because this usually just in most of books you just see these matrices, and usually you don't know where they come from. They come from these basis vectors that are basically rotating, and in the end it's just a conversion between one frame to another. Okay, so there are other transformation matrices, namely we have also scale matrices. So you can have a uniform scale matrix or non-uniform scale matrices. So a uniform scale matrix is, it looks like this. Again, remember these are column vectors, right? So these are the column vectors that represent each basis vector from this coordinate frame. So in this case, you can have a scalar, for example, that let's imagine that the value of the scalar A is 3. It means that you will take every basis vector and you will scale right? Those basis vectors 3 times, right? Basically, what you're doing is you're scaling the entire world, because coordinate frames, what they do is they deform and distort their world. And by distorting the world, they basically distort everything that is inside the world, right? So basically, yeah, so you take all the positions on a 3D model, for example, you multiply by this scale matrix with 333 in this positions, and you will get the same model, exactly the same model, but 3 times bigger, right? And this is what the non-uniform scale matrix looks. So you can decide not scaling like uniformly, but saying, okay, I only want to scale, for example, in the x direction or the y direction or the z direction. So if a, for example, in this case is equal to 1, everything will be exactly the same on the x coordinate, right? On the x basis vector. If b is equal to 1, everything will be exactly the same. They will not change, they will not scale in the y basis vector. But if here we have 5, only on the z direction, only on the z basis vector, it will basically scale everything by times 5. Okay? Any question from this? From now the scale matrices? Okay, so if you have a smiley face composed of points. Yes, if you have a smiley face composed of points in a 2D plane and you want to rotate, just multiply each point by the rotation matrix. That is exactly what you need to do. Exactly, yeah. And the same if it's not necessarily in the 2D plane, right? If you have a 3D model, if you have the raccoon, right, or a bunny or whatever 3D model you have, what we usually do to either scale or rotate objects in 3D in computer graphics is exactly as you mentioned, right? We take every single position from every single vertex on that 3D model and we just multiply those positions times whatever matrix that we want, right? And someone is saying negative would just invert it, right? Yes, exactly. So that is exactly the other matrix, the other linear transformation matrix that we need to talk today. These are the reflection matrices in 3D. So if everything will be 1, it will be an identity matrix, right? And you're not transforming anything, will be no change. But if one of those numbers is, in this case for the x component, is, for example, -1, if it's negative, yes, of course, what you're doing is basically invert the position on x coordinate and you're doing like a mirror effect, right? Like a reflection, right? And if the value, by the way, if the value here is negative, but it's not exactly 1, you're kind of combining the two things, right? Because because it's negative, you're inverting things, so you're doing a reflection operation. But if it's different than 1, you're also scaling, right? Either scaling up or scaling down that axis. So we usually, if we are talking about reflection matrices, we usually use only 1 and just change the sign of those numbers, right? Okay. Okay, someone is saying that is why our... Oh, sorry. The chat is actually moving fast. Okay, Jasmine is asking, before classes, it is possible to get summary slides and learning goals from what will be covered during the class? Well, you kind of have that, right? Because I am uploading the PDF before the class, and the PDF contains the learning goals. But also, I'm already put optional readings for every single lecture on the webpage, right? So if you go to the webpage and see, tomorrow we will cover this topic, you will see that there is a suggested reading there, and you can go there and read that thing, and that will of course be easier for you, right? Yeah, someone was asking about Vec4 coordinates. Those, as Ivo is saying, those are homogeneous coordinates. We will cover that later, so don't worry. We will talk about that on Friday, okay? So for now, this is what we needed to talk today. So let's open the mic. So can anyone wants to not talking on the chat, sorry, not asking on the chat, but asking, raise their hand. Yes. So let me unmute them. Yes, we can hear you.
Hello.
Hello.
So in the usual 3D rendering pipelines, I usually only see just one matrix for incorporating all roll, pitch, and yaw. But what based on the slides you've seen, you can just decompose them into single axis rotation. So do they implicitly actually do composition of single axis rotations, or is there a way to just do roll, pitch, and yaw at the same time without that kind of decomposition?
That is a very, very, very good question. And actually, we'll talk about that. If you see the webpage, there is a topic, I think it's in the next two lectures, that is called composition of transformation or composite transformations. So basically what happens is that once you have transformation matrices, you can multiply them together to get a single matrix. That is what we usually do in computer graphics. So let's talk about, for example, the vertex shader. The vertex shader needs to get the original position from your 3D model. In this case, imagine that you're loading an OBJ and you have positions of that OBJ. Those positions are they are a model. They are basically representing a model matrix or a model coordinate system, right? Those are the positions with respect to the model itself. But then you position that model in a scene, in a 3D world, right? So maybe you have two different models and you move those models and you rotate those models. So now you need to convert the original positions to a new coordinate system that is basically the world coordinate system. And then you have a camera, and now you need to have all the positions for all the objects there, but now with respect to the camera. So you need to do another conversion, right? So you can have different matrices, but the thing is, you can actually multiply all those matrices, and you end up having a single matrix, and then you multiply by your points. The same happens with, as you said, for example, that when you are, for example, making a complex rotation to an object, and maybe you are like, okay, I will rotate this object first 45 degrees on the z-axis, and then I will rotate it 22 degrees on the x-axis. So you can construct two different matrices, right? One for the first rotation and one for the second rotation. And you could take your original points and multiply everything by the first one, and then you have a result, and then take the result and multiply everything by the second matrix. You can do that, but it's easier to first multiply both matrices together, and you end up with a single matrix that basically contains all the transformation in a single matrix, and then you just multiply one time, right? Basically, that is just for avoiding multiple computations, right? So imagine that you have a 3D model with 1,000,000 vertices. Instead of multiplying 1,000,000 vertices times one matrix, and then again times another matrix, and then times another matrix, so basically multiplying 3 times, you just create a single matrix that has every single transformation, and you make one single computation for one of those, for each of those 1,000,000 vertices, right? Okay, yeah, good question. Anyone else? Okay, let me unmute. Yes, so we can hear you.
Oh, hi, Eric. So I have a question. So you mentioned like we can just kind of imagine like a coordinate system being rotating. So that helps you visualize how the rotation matrix works.
Yeah.
Could you kind of like elaborate on that? Because like I was thinking, the rotation matrix is you have one point in one coordinate frame, and rotating it still stays in the same coordinate frame. So I'm just wondering how it relates to coordinate frame being rotating.
Well, this thing of imagine taking a rotation matrix or a transformation matrix and imagine it as a coordinate frame that is rotating is basically as this animation here, right? So in this case, for example, this is a rotation on the x-axis, right? So yes, you can see the numbers, but in the end, the numbers that you're seeing, those columns, are basically exactly the same as the coordinates of the tips of these basis vectors. So a rotation matrix in 3D or in 2D basically is just a coordinate frame whose basis vectors are unitary and orthogonal, right, among them, and yeah, basically rotating that coordinate frame and constructing the matrix using the coordinates of those basis vectors is giving you the actual rotation transformation. I don't know if I'm being clear with this.
Yeah, that makes sense.
Good.
Thank you.
And yeah, so we're almost done. Basically, we're done because we need to again remember that we need to end the lectures at 50. But let me tell you something very quickly, which is super important. So these rotations, the rotations that I'm writing in this presentation, and usually everything in terms of transformation matrices that I will use in my lectures, I will use a column notation. That is why I'm always saying column vectors, column vectors, column vectors, right? So if you go and check, for example, I mean, there are different books in computer graphics, and you can go and check online. There are a lot of web pages that are talking about rotation matrices, right? But the thing is, you can be confused if some of those sometimes are written in row notation. So what happens? In this case, let's talk about, for example, this rotation here, rotation in Z, right? So the way this rotation matrix is constructed is by taking the basis vectors as column vectors, and basically each column is one of the basis vectors. If you're using row notation, this row will be the first basis vector, and the second row will be the second basis vector. So basically what you will have is basically a transpose of the matrix. So instead of having cosine minus sine and sine cosine, you will have cosine sine minus sine cosine. Okay, this is very important because when you actually are coding, right, and you're sometimes having questions and you could just go online, oh, I don't remember how was the rotation matrix, and just copy everything. If you're not aware if they are using column notation or row notation, you can basically use the wrong matrix, right? And the reason I am using column notation is because OpenGL uses column notation for their matrices. So eventually we will see how you actually can do this and code this inside your JavaScript to actually rotate and animate things using WebGL and in your assignments. And those matrices that you will construct, those need to be constructed as column major matrices, right? So this is super important. And I'm always using column major. If you check any other source, either books or whatever, please always check if what you're seeing there is column or row notation, right? Okay, so someone is raising their hand. Yes, so last question for today, I think. No?
Oh, sorry, I should put down my hand.
Okay, no worries. Okay, so no more questions. Yeah, so we can finish. Thank you so much and see you on Friday. Bye, everybody.